This is the first video lecture of the semester. It covers section 1.1 of the OpenStax text. The book calls this section Definitions of Statistics, Probability, and Key Terms. I just boiled that down to key terms. I think that nails what this section is about. This section is about some key terms, some of the important vocab that we're going to have to use throughout the semester. And so you're going to want to put effort into this section, not only because you need to know what these words mean, but also just the effort to stay awake through this stuff. This stuff can be very dry. As a math person, I want to be working with numbers, doing some calculations, doing some interpretation. Here we're just trying to nail down what these words mean so that we can understand them in the future when we're trying to do the actual statistics. First important word of the semester, data. A set of data is a collection of recorded observations. So you probably have some notion of what data is, and we're talking about the same thing here. Data is just a bunch of numbers or words, a bunch of observations. You see something, you write it down. You see something else, you write it down. That's data. Usually that data all relates to the same thing. So a set of data might be a collection of heights of players in the NBA. Or it might be the style of cut of an engagement ring, something like that. A set of data is just a collection of recorded observations. And what we want to do is talk about how we can analyze that data. And the science in which we do that is called statistics. This is the class that you're signed up for. The science of statistics deals with the collection, analysis, interpretation, and presentation of data. And we're going to talk a little bit about all of this in our class. When we talk about collection, we're talking about how we gathered the data. Did we just ask 10 of our friends? Or did we go out and get some kind of random sample from a larger group? Analysis and interpretation kind of go together. When we talk about analysis in this class, we're usually talking about taking that data and boiling it down, finding like an average or a standard deviation. Interpretation goes even deeper and says, okay, now what can we infer from getting this data, from doing this analysis? What does it mean? And then presentation of data usually deals with drawing graphs, making tables, things of that nature. In our class, being a math class, we're going to focus primarily on the analysis and interpretation parts. We will do a little bit about collection. We're going to cover one section on how data is collected. You can take an entire class in that, and believe me, I'm sure that would be a hoot. We're not going to bother with that. We're going to do one section on it because then we're going to have an overlying assumption throughout the entire semester. We are going to do a couple of sections where we talk about presentation of data. But again, drawing and reading graphs is something you've probably done in prerequisite courses, so we're not going to talk too much about that. We're going to focus on the math and the interpretation of that math. So we're going to do a lot with the analysis and the interpretation. And in the middle of the course, we're going to take a break from statistics and talk about maybe like a cousin field of statistics, which is probability. So in the beginning, we're going to do what's often called descriptive statistics, where we talk about calculating means, finding standard deviations, drawing graphs. Then we're going to talk about probability in the second unit of the course. And then we're going to merge those two things together and do what we call inferential statistics, where we use probability to give us a way to interpret what we've done in our analysis. When we gather a set of data, it's usually to analyze some group of individuals. And when I say individuals, I don't necessarily mean people. Those individuals could be objects. The math word that we often use is elements. So individuals could refer to people. It could refer to objects. But a population is the collection of all individuals in the group being studied. So for example, if you wanted to know the mean lifespan of house cats, the population is the set of all house cats, leaving out in area 1. You're talking about all of them. That's the group that you're studying. If you wanted to know the average number of semester hours that Parkland College students take, then the population is the set of all Parkland College students. Populations can be very difficult to work with. They can be either impractical or sometimes impossible. You can certainly visualize a time when it would be impossible, like the house cat example. There's no way you could really track down every single house cat and find out how long they lived. It's just impossible to do. And sometimes it's impractical. So for example, suppose you were running a bakery and you were making chocolate chip cookies. And you were interested in the average number of chocolate chips that wind up in your cookies. You actually could take every single cookie that you bake smash them and count the chocolate chips and get the average. But if you smash every cookie that you make, what are you going to sell? You just destroyed all of your product. It would be completely impractical for you to do that. That would be ridiculous. So, because populations can be impossible or impractical to work with, we often take a much smaller group and use that kind of as a representation of the population. And we call those groups samples. A sample is a portion of the group being studied that is selected to represent that entire population. So what we'll do is we'll select some smaller group. It's usually a much smaller group. Like rather than taking the collection of all house cats, which would be impossible, we'll take maybe 100 house cats. Or rather than smashing every cookie that we've baked, which would be ridiculous, we're going to take 30 cookies and smash them and count the chocolate chips in those. A sample is of some smaller group that's used to represent the population. Now, the way in which you choose that sample might give you good data or bad data, what we call biased or unbiased data. And we'll talk about that later. For now, just know that a sample is some smaller group. For the math nerds out there, it's a subset of the population. And the point of that sample is that it should somehow represent that population. So I've got an example here. I want you to think about it, and then I'll give you the answer. It says, the proportion of all voters who are going to vote for a specific candidate is estimated by choosing 1,000 voters and asking each who they plan to vote for. So it's impossible to track down every single voter. So what they're going to do is they're going to select 1,000 voters and ask them who they plan to vote for, and maybe use that as an estimate for the proportion of all voters who will do that. So this example has a population and a sample. I'd like you to pause the video, think about it for a second, and then I'll give away the answer. The population is the group of all individuals who are being studied. And here we're looking at all voters. So the population is the set of all voters. The sample is some smaller group that's been selected to represent that population, and they're choosing 1,000 voters. They represent the sample. So the population is the set of all voters, and the sample is the collection of 1,000 voters who were selected to represent all voters. Now you'll notice there was a word in there that seems kind of mathy that I ignored, and that's proportion. The proportion is a number that's somehow related to these voters. It's not part of the population, though. The population is the group of individuals. So the population is the set of voters, and from that set of voters, we're going to calculate some proportion. In particular, we're going to calculate the proportion who are going to vote for somebody. That number has a word. Because that number represents an entire population, we call that a parameter, and that's our next key term. A parameter is a numerical value that summarizes the data for an entire population. A parameter could be something like a mean or a proportion or a standard deviation, but it's a mean, proportion, or standard deviation for the entire population. So in the previous example, the parameter would be the proportion of all voters who are going to select that candidate. Now we've already said that tracking down an entire population can be impossible or impractical. So similarly, a parameter can be very difficult to calculate. You won't usually have data for the entire population. So what we're going to do is we're going to gather a sample. We're going to take the data from the sample and we're going to summarize that. And that's what we call a statistic, and it's where the name of the science comes from. A statistic is a numerical value that summarizes the data from a sample. So we admit that we can't track down the data for the entire population. Instead, we select some much smaller representative group, or at least hopefully representative group. We gather the data from that smaller group, that what we call the sample, and we summarize that data, and we call that a statistic. This is one of those subtle differences that you'll want to keep straight. A parameter is for an entire population, a statistic is for a sample. And I'm going to make an ass out of myself to help you remember this, but it's alliterative. A parameter is from a population, whereas a statistic is from a sample. And you're not allowed to forget that now. I will hate you forever if you forget that, because I just made myself sound like an idiot to help you remember. So you've got to remember this difference. Not to mention that it's important for the class. It's so important that I've written it in almost blood red on the next slide. The overarching theme of this course is how we can use a statistic to estimate a parameter. Basically, everything we're doing in this class is building towards how we use a statistic to estimate the value of a parameter. We often can't calculate parameters. When you hear somebody say something like 46% of all Americans have this opinion, they didn't really ask every American. What they did was they gathered a sample, and from that sample they're making an estimate. Whether or not that estimate is a good estimate has to do with how the sample was gathered, how big the sample is, and we're going to talk about all of that stuff. Basically, what this whole class is about, what we're building towards, is how to use a statistic to estimate a parameter. We're also going to talk a little bit about testing claims about parameters, but that's in the same vein. It's a very similar idea. Let's go back to our previous example and see if we can tell the difference between the parameter and the statistic. It says the proportion of all voters who are going to vote for a specific candidate is estimated by choosing 1,000 voters and asking each who they plan to vote for. Now we said the population was all voters. And the parameter is a number that somehow summarizes that population data, the data from the population. Well, if the population is all voters and we're going to find a proportion for those voters, then the parameter would be the proportion of all voters. And you can't stop there because the proportion of all voters who what? Like to eat cheese? Have back hair? No. We're talking about the proportion of all voters who are going to vote for that candidate. The parameter is a numerical value that summarizes the population data. The statistic is a numerical value that summarizes sample data. Now we already said that the sample is the collection of 1,000 voters. The statistic needs to somehow estimate the parameter. The parameter is a proportion, so the statistic should probably be a proportion. I should mention really quickly, even though you probably don't care, that the statistic does not have to be the same kind of measure as the parameter. If you wanted to estimate a mean for the population, you might use a median for the sample, or vice versa. Those measures don't have to match. But here, that's the obvious thing to do. The statistic here would be the proportion of the 1,000 voters, let's say the 1,000 selected voters, who will vote for that candidate. The parameter is a number that summarizes data for the entire population. In this case, it's the proportion of all voters who are going to choose that candidate. And a statistic is a number that summarizes data from the sample. The sample is the 1,000 voters who were selected, and the obvious thing to do here is to find the proportion of them who are going to vote for that same candidate. I want to do a second example distinguishing between these two, a new example where we have to work it through all the way. So it says the mean weight of all pizzas made at Papa Del's is estimated by calculating the mean weight of 16 randomly selected Papa Del's pizzas. Man, I don't know why I made this example up. It's just going to make me hungry. Okay, so the goal of this is to figure out what is the parameter and what is the statistic. But before we can do that, there's a sub-goal, and that's identifying what is the population and what is the sample. Pause the video for a second and see if you can identify the population and the sample. And if you feel confident, go for the parameter and the statistic as well. So the population here is the collection of all pizzas made at Papa Del's. Because we're studying pizza made at Papa Del, the population is the collection of all pizzas made there. That's what we're curious about. The sample, therefore, is the 16 randomly selected Papa Del's pizzas. And you'll notice this time I threw in the word randomly. We're going to talk about why that matters later. It doesn't matter for identifying these key terms. The population is the set of all pizzas made at Papa Del's. The sample is the 16 randomly selected Papa Del's pizzas. Now that we have that down, we can identify the parameter and the statistic. The parameter is a number that somehow describes the entire population. What we're curious about is the mean weight. The mean weight would be a number. So the parameter is the mean weight of all Papa Del's pizzas. The statistic would be a number that summarizes the sample data. The sample, we said, was the 16 randomly selected pizzas, and again, we're going to calculate the mean here. So the statistic is the mean weight of the 16 randomly selected Pappardell's pizza. The parameter is a number that describes the entire population. The statistic is a number that describes the sample. And you might have follow-up questions like, can you really get good information from only taking a sample of 16 individuals? We'll talk about all of that later. It turns out that you can still get really good information from a small sample size like that. We'll talk about how confident we can be in our estimates and things like that later in the course. For now, though, don't focus on that too much. I want you to focus on these key terms: population, sample, parameter, and statistic. One thing I want you to notice that I included in each of my descriptions here is the thing that we're measuring. Right? We've talked about the population being the individuals that we're studying and the sample being the smaller group taken from the population. We've talked about the fact that the parameter is a number like the mean, some summary of the data. We also have this other piece, which is the thing that we're interested in. Right? We call that a variable in statistics. And I know when you think variable in math, you think like X, Y, Z, something like that, something you have to solve for. But we call this a variable because it's the thing that varies from individual to individual. A variable is a characteristic of interest for each individual of the population. It's the thing that you're interested in, what you want to know about. In the voting example, it was who the voter is going to choose. That will vary from person to person. In the pizza example, it's the weight. The weight of each pizza is going to vary based on its size, based on its toppings, just by chance, because the person making the pizza might have put just a little bit more sauce or a little bit less cheese or whatever. Those are the things that vary, and so we call that a variable. One of the last things that the authors bring up in this section is distinguishing between two types of variables. And the reason this analysis is important is because we often do different things for the two different types. There are different graphs that you draw for the two different types. More importantly to us, there's one set that's a little more mathematical than the other. The two categories of variables are categorical and quantitative. Variables can be categorized as categorical or quantitative. And you'll notice that in my slide here, I've put some words in parentheses. Another common name for categorical variables is qualitative. Categorical and qualitative can be the same. Your author actually uses numerical in this section and then quantitative in the next section. And I prefer the term quantitative, so that's the one that I'm going to use. What is the difference between these two? I'm not going to write out the formal definitions here. I'm just going to give you a quick breakdown. A categorical variable basically describes the individual or identifies the individual without assigning value. A quantitative variable, as the name kind of suggests, gives some sort of quantity to a characteristic. So this counts or measures a characteristic of the individual. So this is kind of cheating to say it this way, but a quantitative variable gives a quantity to the characteristic. A categorical variable simply describes or identifies without quantifying. That's the main difference. Let's do a set of examples to distinguish between the two. First, brand of shoes that you bought last. Right? So think about what that data would look like. You go around asking people, hey, what was the brand of shoes that you bought last? And what are your answers going to be? They're going to be words. They're going to be things like Nike, Adidas. I'm a dad, so I'm rocking the New Balance, right? And then you didn't ask for the number of shoes they bought. You asked for the brand of shoes that they bought. The answer is going to be a word. And when the data consists of words, that's definitely categorical. That is not quantitative in any way. Second example, the amount you spent on tuition. This is a number, a very important number. And it quantifies something. It's the amount that you spend. You can count it. It's something that's counted. It's being given a quantity. This is quantitative. The number of COVID cases in the US, again, it says number. You can pretty much tell. It's quantitative. The state where you were born, the answer is going to be a word. That's not a number at all, and this is categorical. But the next example demonstrates why I don't like the term numerical, and I might be giving the answer away. But it says the zip code of your mailing address. Now your zip code is a 5-digit number, right? The zip code where your mail goes to is a 5-digit number. Like mine right now is 61822. But that doesn't quantify anything about me or my location. It just identifies. It's just a way to identify a location. It doesn't give value or quantity in any way. It's just used to identify. So this is categorical. Examples like this can be tricky. So there's kind of a secondary way to distinguish between the two. If a variable is quantitative, then you can talk about things like averages and differences. They'll make sense in some way. For a categorical variable, you can't do anything with averages and differences. Either it's impossible to calculate them because you've got words, or they're meaningless. All right, let's go to the zip code example again. I've lived in a bunch of different zip codes in my life. I currently live in 61822. My college zip code was 61920. I lived in the middle of the Mojave Desert. Right? I grew up in Auburn, Illinois for a few years. Right? There's 4 of my zip codes from my lifetime. If I added those 4 zip codes together and divided by 4 and got my average zip code, what would that mean? Right, it doesn't mean anything. You can't talk about my average location by taking my 4 zip code and finding the mean. That doesn't tell you anything, right? Or if I subtract 2 zip codes. If I took your zip code and subtracted my zip code, does that say how much better one location is than the other? No, that doesn't mean anything. That difference is meaningless. So with quantitative variables, you can find averages. You can talk about average tuition or the average number of COVID cases over time or something like that. Right? You can talk about the difference in the number of COVID cases because they've gone up or they've gone down, or the difference in tuition, who's spending more money. There, the averages and differences make sense because those 2 variables are quantitative. But with categorical, you either can't do it, like you can't find the average shoe bought, that doesn't make any sense. Or even if your data consists of numbers, those numbers aren't quantities, and so the differences and averages don't mean anything, like zip code, or like telephone number. You can't find the average telephone number, social security number. Those averages and differences would be meaningless, so those are categorical. Be sure to spend some time reviewing these definitions. Make sure you know the difference between a population and a sample. Make sure you know the difference between a parameter and a statistic. Make sure you know the difference between categorical and quantitative. If you have any questions, shoot me an email or see me in an office hour.